All right, welcome again to Advanced Modeling Methods. And this is lecture 16, right?
Yes.
And lecture 16, and on the previous lecture, we stopped. Well, we're looking at what we do when we have a Poisson equation, right? So we casted our Poisson equation again. As the Laplace of t is equal to minus b of x, where this function b of x is known, right? And that represents generation. In a heat conduction problem, that represents energy generation per time, per unit volume within the medium. And it has a different meaning depending on the type of potential problem that you're working with. If you're working in electrostatics, or if you're working on ideal fluid flow, or if you're working on any other type of potential theory, that right-hand side term has a different meaning, but it has a physical meaning nonetheless. All right, so we basically, well, these basically led to, let me rewrite the equation just in case. Rewrite the equation. All right. So these basically led to, let me write the whole thing here, C T, okay, and when I say the discretized boundary integral equation would be like this, plus the summation from j equal 1 to n of t j h I j is equal to the summation from j equal 1 to n q j g I j plus b of psi I, such that b of psi I is equal to the integral over the domain of dx times g of x and psi I over the domain. All right? So this is a term that we have to deal with. That's different from what we had before. And notice that that term includes a domain integral. And anytime we see a domain integral, there's a problem because we call this the boundary element method for a reason. We want to push everything over to the boundary. All right? So we concluded that if this function b, which is given, happens to be distributed sources, that integral goes away. It vanishes, right? So we don't have to worry about it. If that function b happens to be a constant, there's a way for us to actually play some algebra and eliminate these. Not really eliminate it, but turn it into boundary integrals. Okay? Using Gauss's divergence theorem, we can turn that into boundary integrals as long as this b is a constant. Okay? Now, what if it's a general function? Okay, we cannot make any assumptions as to what that function is. Let's say it's a sine, a cosine, exponential, whatever function. There is no general way of using Gauss's divergence theorem to make it work. Okay, so if b is a general function of space x, the domain integral cannot be directly transformed into boundary integrals. So we're going to look at an indirect way of doing so. An indirect way of transforming the domain integral into boundary integrals is through the use of the dual reciprocity method. Dual reciprocity method. Okay, so we call this now the dual reciprocity BEM, boundary element method. And it's a method that it was originally formulated to deal with that right-hand side function, but it was later generalized for other things. And it's actually very useful, because it turns out that you can apply for when the equation is transient, when you have an extra term on the right-hand side that deals with storage, like the TDT, when you have other types of equations, when you have things on the right-hand side that you cannot handle, you cannot deal with, you dump it to the right-hand side, assume it is a function, and deal with it using the dual reciprocity method. And let's explain how this works. It's actually quite simple, but quite powerful at the same time. And it retains the nature of the boundary element method as it passes everything back to the boundaries. Okay? There's some things that need to stay in the interior, but you don't need to integrate it. So as long as you avoid having to integrate the interior because you don't want to mesh the interior, it's fine. Okay? So there's some things that need to be evaluated in the interior but not integrated, and then all the integrals are passed to the boundary, and therefore you can use the same framework, the boundary element discretization and so on. All right, so what we're going to do is we're going to let b of x, which remember is a known function, it's the right-hand side, be expanded in terms of known expansion functions f of x, fk of x. So we have k different functions and coefficients alpha k to be determined, such that, so we're going to let b be equal to summation from k equal 1 n plus ni of alpha k fk of x. This is a very simple expansion. And the function k, f of fk can be polynomials, for example. We can pick k different polynomials. And notice that we need as many as number of points on the boundary, number of points in the interior. Again, remember, n, number of boundary points, boundary nodes, and ni, now number of interior nodes. Okay, but these interior nodes, although they're in the interior, we don't have to do any discretization, we don't have to do any meshing in the interior to be able to use them. So basically, if this is your domain, you're going to have some boundary elements, and then you're going to have these points on the boundary. Those are the nodes that correspond to the center of each element. So these are the dots. And the interior ones are going to go like wherever they may go, as long as they're in the interior. And by the way, we already have a routine in the code that can distribute points evenly in the interior, right? And determine when the points are, in fact, inside of the domain or outside of the domain, and discards the point that are outside. So these are these ones. All right. So F, K are N plus Ni linearly independent arbitrary functions. Linearly independent arbitrary means that we pick what they are. Again, they can be i.e. polynomials, such that, for example, f1 of x is equal to 1, f2 of x is equal to x, f3 of x is equal to y, f4 of x is equal to x squared, f5 of x is equal to x times y, f6 of x is equal to y squared, and so on and so forth. As many, you can just keep constructing the Pascal triangle in terms of two-dimensional polynomials, and this is in 2D. If you were in 3D, you need x, y, and z. Okay, because remember the x dependency contains the dimensionality of the problem. X, xy, or xyz if you're in 1D, 2D, or 3D. All right, and all these functions are linearly independent of each other, and they're arbitrary, they're known, and all you have to do is just use them and find those coefficients alphas that expand or interpolate a function B. Okay? That you would do any other interpolation. Find the alphas so that when you impose these arbitrary functions, this function B is properly interpolated. For instance, that's an example of what functions you could use. All right, so let's just stable that for a little while. Let's assume that we know the functions f, which we do. We pick them. Now, furthermore, require that the functions fk of x be equal to some functions uk of x. The Laplace of some functions uk of x. Okay, can we do that? Arbitrarily? For any function? If we arbitrarily decide that f's are going to be 1, x, y, x squared, y, x, y, y squared, so on and so forth, in that order, right? What would be the functions whose Laplace are equal to those? Well, you can just integrate twice, right? Integrate the first one twice with respect to x and with respect to y and so on and so forth, you'll find what u is. Integrate the second one, this one with respect to x twice and with respect to y, and you'll find what the second one is. So that when you take the Laplace of the resulting function, you get fk of x, right? So, i.e., for the selected polynomials, for instance, who would be u1 of x? A function who, if we take the derivative with respect to x twice and the derivative with respect to y twice, we get equal 1. For instance, how about x squared plus y squared over 4? How about that function? Wouldn't that give you 1? If you take the, that's an example, right? There's a few more. Right? So if you differentiate this with respect to x twice, what do you get? 1/2, right? If you differentiate with respect to y twice, what do you get? 1/2. 1/2 plus 1/2, you get 1. All right. How do we get x? We need an x cubed, right? So I would put an x cubed here, and I will divide this. I will divide it by 6, not by 6, yeah, by 6, and that will give me x, and then I will say y. How about that?
It goes 1 and then 0.
Yeah.
Professor, so when we're taking the derivative with respect to x, wouldn't the y cancel out? Like for the first one, where it shouldn't go to 0? Yeah, when you said it with y, when you differentiate y with respect to x again, it shouldn't also be there. Alright.
What's the Laplace of a function?
Double integral.
No, it's not the double. The Laplace of a function is the derivative of u with respect to x squared plus the derivative of u with respect to y squared in 2D. Right?
Yeah.
Okay, so if you take this function, differentiate it twice with respect to x, what do you get? 1/2. And if you take this function, differentiate it twice with respect to y, what do you get? 1/2. If you add the x double derivative plus the y derivative, the double derivative, you get 1. Same thing here. If you differentiate this with respect to x twice, what do you get? X, right? If you differentiate this with respect to y twice, what do you get? 0. So the Laplace of these is indeed x. Okay? And you can determine these functions automatically. You don't need to do it by hand. You can do y cubed over 6 plus x. That'll be easy. And you can continue. This will be 3. And so on and so forth. Alright? So as many, obviously if you have 20 boundary points in your problem and 100 internal points, how many functions are you going to need? 120, right? Okay, you need as many functions as you have points, boundary and interior points. So you need 120 points. So you're going to have plenty of these polynomials all the way to order, I don't know, 50 or so, right? And then you need the Laplace of that, or you need the anti-Laplace of that. You need functions whose Laplace are equal to that, which you can calculate automatically. At the end of the day, we're not going to use polynomials, okay? So I'm just giving you an example of how arbitrary these functions can be. You can pick whatever you want. When you're expanding a function into other functions, you can pick whatever you want. What is a Taylor series? A Taylor series is an infinite polynomial expansion of any function, right? You pick any function in the world you want, a sine, an exponential, and you can, Taylor says that you can expand it in an infinite series of polynomial. Exactly, right? That means you can get the function exactly the way. What is a Fourier series? Fourier series is an expansion of any function you can think of in terms of sines and cosines. It seems weird, and they call them crazy when they came up with this idea, that you can take a nice-looking, smooth function and represent it by sines and cosines to actually infinitely oscillate. Well, he said that in the limit of infinity, all these oscillations cancel out, and you get your smooth-looking function. Well, it was hard to prove back then in the 1800s because there were no computers, and there was no way you can actually evaluate things to infinity, but he was right. We can do it in the computer now and see how all these wavelengths and amplitudes actually eliminate, cancel each other out, and you can have whatever function you want, even discontinuous functions, okay? And these discontinuous functions can be easily expanded in terms of sines and cosines. So these functions can be arbitrary, and they are the Laplace of other functions who are also arbitrary. They're connected, but they're arbitrary. Okay, at the end of the day, we're not going to use polynomials because of the fact that polynomials, what happens? Well, if you have 1,000 points, then you need a 1,000-degree polynomial, right? And the 1,000-degree polynomials are pain in the neck to handle because you need to evaluate them and so on. So we're not going to worry about it. We're going to find an alternative to this. All right, so the point is the following. So the function v of x now becomes the summation from k equal 1 to n plus ni of alpha k times the Laplace of uk of x, whatever they are. We agree with these, right? All right. We still haven't determined alphas, but we know we can do it. Let's just don't worry about it for now. And the term b of xi I, which is the term on the boundary integral equation, now becomes the integral over the domain, which is what we don't want. We don't want to see a domain integral of b, which is now the summation from k equal 1 to n plus ni, alpha k, Laplace of u k of x, and let me put this in brackets, and here's your Green's function, the omen. All right, so these alphas and the summations, well, the integral of the sum of something is the sum of the integral of something, and the alphas are constants, we can take them out. So basically we can say that b of psi is equal to the summation from k equal 1 to n plus ni, alpha k, Laplace of u k gx psi I d. All right. So what can we do with that integral? It has a Laplace of something times g. That looks like the original equation, Laplace of temperature times g. That's how we started everything, right? We have an equation that says the Laplace of temperature was equal to 0. We multiply it times g, integrate it, and then apply Green's second identity, right? Which is integration by parts. If we apply integration by parts here twice, then we might be able to get rid of these domain integrals. Apply Green's second identity, which remember is nothing but integration by parts twice in space. And what do we get? Summation from k equal 1 to n plus ni, alpha k is equal to, and this would be the integral over the boundary of duk dn of x times g of x and xi, d gamma, and minus the integral of uk of x times dg dn x of xi I d gamma plus, and this would be the integral over the domain of we have u k of x times the Laplace of g of x xi I d gamma, d omen. So that's hence the name dual reciprocity. We're doing to the right hand side what we've already done to the differential equation. Apply Green's identity. All right, and then we know this term here we call h, right? The normal derivative of g we call h. We're gonna call this term here p. And remember what the Laplace of g was? So let du dn be equal to p. Remember we know u and therefore we know p. We're going to let dg dn of x and xi be equal to h, which we've done before. And recall that the Laplace of g of x and xi is equal to minus the Dirac delta function of x and xi. That was by definition. That's how we ended up with the equation in the first place. So B of psi I is equal to the summation from k equal 1 to n plus ni of alpha k. Now we have the integral over the domain of pk of x, g of x and xi, psi, minus the integral over the boundary of uk times h of x and xi. And this integral right here, which is equal to the derivative of the function, it goes away because we're multiplying now a function times the derivative of the function. This will be minus c times uk at xi I. And now you can see that the entire information has been sent to the boundary. So the domain integral has been effectively transformed into boundary only integrals. So we have boundary only integrals, which is what we needed to begin with, because our framework, the structure of our code, we only wanted to handle that. We only want to do discretization on the boundary. However, we need some internal points, but those internal points are just for evaluation purposes. Notice that we have summation over number of boundary nodes and internal points of the alpha k. So we need as many alphas as boundary and interior points, and this evaluation is going to take place for boundary and interior points, but the integration only takes place on the boundary. All right. So we're going to put this back into the BIE. Back into the BIE, and what we have is C of psi I, T of psi, plus the integral over the boundary of T x H x psi I d gamma is equal to the integral over the domain of Q x Gx and psi I d gamma plus the summation from k equal 1 to n plus ni alpha k, all these times the integral over the boundary Gx psi I d gamma minus the integral over the boundary uk of x h of x comma psi I d gamma minus c of psi I uk of psi I. Now discretizing and letting T, Q, U, and P be constant across each boundary element, delta gamma j. We've done this a few times already. plus the summation from j equal 1 to n of tj times hij is equal to summation from j equal 1 to n qj gij plus the summation from k equal 1 to n plus ni of alpha k of the summation from j equal 1 to n of p j k g I j minus the summation from j equal 1 to n of u k j h I j minus c of xi I u k of xi. This is a discretized version of that equation.
I forgot the reason, but why do we put the little hat on the H?
Because then we combine the c with the h and call it just h.
Oh, okay.
Yeah, we add the c's to the diagonals of h hat and just call it h.
Oh, okay. So this is just like the previous.
Yeah, it's an intermediate step of h. Okay, so again, we're going to collocate I at I equal 1 through n boundary nodes. What do we have? And let hij be equal to hij plus ci times delta ij, and that's not the direct delta function, it's the Kronecker delta, basically adding ci to all the diagonals of hij will make hij. So we have summation from j equal 1 to n of hij times tj is equal to the summation from j equal 1 to n of gij times qj plus summation from k equal 1 to n plus ni of alpha k of the summation from j equal 1 to n of gij times p j k minus summation from j equal 1 to n of hij times uj. Okay. So notice that all we need to do is evaluate the k different functions u, which we know, these are the arbitrary functions u, evaluate them at the boundary, take the p functions, which we know, these are the normal derivatives of the u functions, which we know, there are k of them, or n plus ni number of them, evaluate them on the boundary, right? Multiplying by the already existing gij and hij influence coefficients, which we already determined by integration. And we have them in two matrices already. So everything here is known. All of these is known. Right? U is arbitrary functions. P is the normal derivatives of these arbitrary functions. And we have what we need. We're missing the alphas, though. So, let's see. And this is for I equals 1 through n. Now this in matrix vector form B is we have H, which is in the size n, comma n, times T, which is size n, comma 1, is equal to G, which is size n, comma n, times Q, which is size n, comma 1, is equal to, or sorry, plus, and I am going to send this over to the right hand side. Let me see if I can fit all these here. Actually, I'm going to do it first like this. Summation from k equal 1 to n plus ni of alpha k times g, which is again size of n by n, p k, which is the size n by 1, minus h, size n by n, and u, k, which is the size n by 1. Furthermore, I'm going to continue this. H, n by n, t, n by 1 is equal to g. So notice the dimensionality is still the size of the boundary. It's just that the right hand side has this, which will be, I'm going to put this into a big G. Actually, I'm going to put it in brackets. G, which is of size n by n. And now I am eliminating the summation, so I'm going to block this into a matrix P, which is of size n, comma, n plus ni, minus h, which is size n by n, times a matrix U, which is of size n, comma, n plus ni. Remember, we have n plus ni functions U, and therefore n plus ni functions P. We've eliminated the summation. And when I multiply this matrix times this matrix, what is the dimension of this resulting matrix? N, comma, n plus ni, right? So the inner dimensions cancel out. They have to be compatible though. So this is of size n, comma, n plus ni, and this multiplies a vector alpha that is of size n plus ni, comma 1. So the result of this operation is dimensionally compatible with this, because this will result in an n by 1 vector. This is an n by 1 vector. And an n, comma, n plus ni matrix times an n plus ni, comma 1 vector is an n, comma 1 vector. All right. So all we need to do is get the alphas. And we're in business. All we need is the alphas, right? Because everything here is known. These functions are arbitrary. This is a normal derivative of these arbitrary functions. G and H we've already determined. These are the same, no difference. Okay? All we need is the alphas, and then we have the vector we need to add to the right-hand side. This is just an extra vector that contributes to the right-hand side. Nothing more. All right, so how do we determine the expansion coefficients alpha k? And we have n plus ni of them. Now recall where we started. Recall that the function b right? Which is the right-hand side function of the equation, which is a known function. We know what that function is. It's equal to the summation from k equal 1 to n plus ni of alpha k times fk of x. All right. So if we have functions f, which we know, and function b, which we know, and then we have n plus ni alphas to be determined, what do? We set up a system of equations, right? We've set up a system of equations that is n plus ni times n plus ni. Okay, so what we do is just basically collocate, evaluate b of x and fk of x at all n plus ni nodes. Right? Leading to the following. Leading to a vector b, which contains n plus ni, comma 1 evaluations. These are the n plus ni evaluations of this function at all the boundary and interior nodes is equal to f, which is the evaluation of this function fk at all the boundary and interior nodes. So we have n plus ni functions evaluated at n plus ni locations times alpha, which is n plus ni, comma 1. Okay? So this is known. This is known. F, remember, are the arbitrary functions. We can take all those functions and evaluate them wherever we want to. We just decide to evaluate them exactly at points k equal n plus ni. Set up a simultaneous systems of n plus ni equations to find the alphas. Solve for alphas by Gaussian elimination, inversion, LU decomposition, etc. Whichever method we want. We obviously select LU decomposition because we already have it in the code. So all we need to do is form another matrix and another vector, pass it over to the LU decomposition routine, and there we have it. We have some alphas. Okay, so solving for alpha is very trivial. What we need to do is solve a system of equations. It comes directly from how we set up the problem to begin with. You understand how we go from here to here? Okay? To set up a system of simultaneous equations of the same size. How many unknowns we have? We have n plus ni alphas to be found. So how many equations we need? We need n plus ni equations. Where do we get those equations? Well, we evaluate the left and the right hand side at each of these points. Okay? We start with point 1, wherever that is. Evaluate the right hand side, evaluate the left hand side. The right hand side here we have alpha 1 multiplying f1, alpha 2 multiplying f2, alpha 3, all the way to alpha n plus ni multiplying the last function evaluated at that point is equal to b evaluated at the first point. That's equation number 1. Then you get equation number 2, equation number 3, evaluate at all the points, all the way to when you get to the last one of the points, interior points, you get a system of equations, a square, and you solve it. The only problem here is that the system of equations is larger than the H and G system of equations, right? Because the H and G system of equations doesn't have the Ni, right? So this is substantially larger because the number of points in the interior can be an order of magnitude larger than the points in the boundary. If you use, say, if you have a square domain, right, and you use, let's say, 10 points aside, that's 40 points on the boundary, how many proportional points will you have in the interior? 100, right? 10 by 10, 100. Say they use 100 points on the boundary, on each segment, on a square. That's 400 points to describe the boundary. How many points are there in the interior? 100 times 100 is 10,000. So now you're talking about a 10,400 by 10,400 system of equations rather than a 400 by 400 system of equations. Okay, that might be an issue. Okay, so that we can keep under control. We obviously don't need that many points in the interior to be proportional to the points on the boundary. We elected to do that for post-processing purposes, so that when we visualize a solution, it's smooth looking. But we can actually live with a coarser distribution of points in the interior. Okay, we don't need that many points to describe what's going on. But the point is that we've actually sent everything over to the boundaries. There's no need for internal integration or domain integration. There's no need for polygonalization, for meshing or anything like that. It's just evaluations of points. And we took advantage of the dual reciprocity to send everything back to the boundary. There's no more influence coefficients to be determined. G and H, we've already determined. It's just the evaluations of functions that are arbitrary. All right, now the key question remains is what functions to use. I talked about polynomials. Those are easy. We can integrate polynomials or differentiate polynomials as many times as we want to. Okay, they are easy to arbitrarily select. They're easy to bookkeep. Okay, if you need 100 polynomials, you can go from polynomial of order 1 to polynomial of order 99. No big deal. If you need 1,000 of them, you can go from polynomial of order 1 to polynomial of order 999. That's 1,000 polynomials who are, in fact, linearly independent of each other. Okay? Now, the problem with polynomials of a high order is that they tend to oscillate too much, and then it adds instability to the solution. But that really doesn't matter because you're integrating them, and once you integrate something, even if it's unstable, that instability actually washes off. That's a nice thing of integrating things. Okay? Methods that don't rely on integration, that rely on a strong form of an equation, like the finite differencing method, it's just pure collocation. You rely on the differential equation, you evaluate it at points, do finite differencing approximation. If you introduce instabilities, those instabilities propagate. But when you integrate, those instabilities are actually washed away. Okay? It's a good thing. So we can effectively select polynomials and get answers, but it's just a little painful or not mathematically correct. It's mathematically correct, but not rigorous to actually use polynomials of n order. Okay? So we need to come up with an alternative to those functions. Functions that we can select arbitrarily, that do not have limits in terms of how many we can use, because we can end up with 1,000,000 points, and we need 1,000,000 of those functions. Okay? And we need functions that are integrable and differentiable. Okay? Because from f we need to determine u, and from u we need to determine p. So we need to integrate and differentiate. So what we do what expansion functions f are favorable for these applications. And the answer is, well, polynomials are not. So what we do, do these, okay. Second, here we are. All right, so what we do is select, use radial basis functions. These are very famous, very popular, very powerful functions that are used anywhere. They're actually over 100 years old, and they were originally used to describe topographies. Okay? These are functions that satisfy all these conditions that I set forth, and are really good at interpolating fields that are quite scattered. Okay? Like topographies, for example. So we used decades ago for that, and now they're being used for solving differential equations like we're trying to do in this case. And in the next section of the semester, we'll see how we can use these functions directly to solve differential equations. Okay, so what are radial basis functions? These are functions that rely on the radial, which is basically the Euclidean distance between the field point to any pole xk. So basically, a function k of x would be a function that depends on the radius k, or the radius from point x to point k, such that in 2D, our k of x is equal to x minus xk squared plus y minus yk squared. That's it. So we pick functions that only depend on radius, but that's the radius with respect to a selected pole. And these functions will end up being linearly independent of each other, infinitely integrable, infinitely differentiable, and would satisfy the condition of being able to interpolate a field whichever way we want. Okay, so there's a few classes of RBF, types of RBF. Ones are called the polyharmonic RBF. The polyharmonic RBF are given by calling this f of k of x is equal to either r k to the power of 2n minus 1, or rk to the power of 2n, by the way, times the log of rk over c. That's called a polyharmonic spline. It's just either where n is any number, n can be any integer larger or equal to 1. All right, so I can pick n equal 1, i.e. n equal 1, then the function k of x is just simply rk over c. For instance, I'm going to talk about what c is in a minute, but let's just assume it's a constant. Two, the multi-quadric RBF. This one looks like this. F k of x is equal to rk over c squared plus 1 to the power of n minus a half. Where n integer greater or equal than 0. Right? So an example, n equals 0 will lead to fk of x being equal to 1 over the square root of rk over c squared plus 1. And this is called the inverse multiplier. All right. And 3, the Gaussian RBF where the function f of k is equal to e to the rk over c. All right, so in 1, 2, and 3, C is an arbitrary parameter that controls the shape of the functions. The larger C, the flatter the function. In all cases. The larger C, the flatter the function. All right, so now we have functions that are arbitrary, that we can use anywhere we want to, that will not require us to come up with high order polynomials and higher. If we have 1,000 points, we don't need 999 order polynomial. We don't need polynomial order 1, polynomial order 2. We need 1,000 functions that look exactly like this, where the only difference between them is the pole with respect to this r is being calculated to. Okay? This r is just basically a distance between any point x to a pole. And that pole corresponds to the location of the point K. All right, so how good does this do? Say, for example, let f of k be a mixed polyharmonic RBF, that's you, of order n equal 1 and n equals 0. So that would be let f of k, which is valid, be equal to 1 plus r k over c. So we put order 1, order 0. Order 1, order 0. That's an example, and that's widely used. This one is very widely used. Okay? And here, for the sake of demonstration, I'm going to let c be equal to 1. So the function f k of x will be equal to 1 plus rk. And therefore, the function fk of x is simply 1 plus the square root of x minus xk squared plus y minus yk squared. Okay, now remember we need how many of these? We need n plus ni. right? We need as many of these as we have boundary points and interior points. Okay? They're all there. Okay? The first one of them is the one where these point xk and yk is the first point. You take whatever other point you want and refer to that point, that's a completely different function. That function is completely different and completely independent from the function, the first function when evaluated at the first point on the boundary here. If you evaluated at the interior point here, put that pole there, that is a completely different function of x and y. Okay? The good thing too about these is that not only you came up with functions that do not change in scope and size and order, they're all of the same order, they're rational functions of order 1/2, right? Irrational, that is, of order 1/2. They're all the same order, they're integrable and differentiable, but the other good thing is that they are simply a function of r. Okay? Therefore, if we need to find uk of x such that fk of x is equal to the Laplace of uk of x, that's even easier than polynomials. Recall, these are radial only functions, and therefore the Laplace can be expressed in polar coordinates. So basically, we have fk of x will be equal to 1 over r ddr r duk dr plus 1 over r squared d second uk of x d theta squared. Where this one goes away because the function u is also expected to be only radial. So 1 plus rk is equal to 1 over r ddr r duk dr of x. So in order to find uk, all we need to do is multiply by r, integrate, divide by r, integrate. Right? Integrating twice. uk of x is equal to, up here, rk to the power of 2 divided by 36 times 4rk plus 9. And recall that pk of x, which is equal to du k dn, is equal to du k dx times nx plus du k dy times ny. So it's just a matter of differentiating that with respect to x, with respect to y. Remember, r contains x and y. It's just an irrational function. And that's it. And those are radial basis functions. And there is a complete spectrum and line of research on radial basis functions, and scientists around the world using radial basis functions to solve differential equations directly. All right, so this is a very brief introduction to the dual reciprocity method. But as I mentioned, dual reciprocity method, it was first developed to handle that right-hand side of the equation. It pushes everything to the boundary, except for evaluations in the interior, which is just evaluation, so we don't need to discretize or mesh anything on the interior. But it was later found, generalized, to solve much more complicated problems, like transient problems and problems where the right-hand side would actually be a function of temperature, and nonlinear problems. We push everything to the right-hand side, call it a B, and then we deal with it using radial basis functions in the dual reciprocity method. All right? So when we get back from spring break, on that Tuesday, we will implement this dual reciprocity method, or we'll take the code that we already wrote in Fortran, and we just add one routine that does this. So we can have a general function B, and the code will be able to handle it. We can have any type of internal generation. All right? Then we'll have the Thursday after spring break, we won't have class because it's when you have to turn in your project. You have a free day there to the project is due by midnight. And then as we get back from that, the following week we'll start meshless methods, which is basically take everything that we've done and eliminate all the integrals. Okay, keep everything meshless, no mesh, neither on the boundary nor on the interior, and see if you can handle it that way. See if you can do it that way. All right. So have a nice spring break. Be safe, and I'll see you in a week and a half.
Super glued my finger, but I also used you can spray it with this accelerant, and apparently it gets it real hot.
You burn your finger?
Yeah, it felt like I was touching a soldering iron, but I couldn't get it off my hand because it was super glue.
True winner.
Feeling better now.
Be safe.